interact well with people in natural language, in a large part, is like getting them to think like we do, not just use the language, but to use it in ways to convey ideas that are the ideas that we have. And my research and teaching work is focused on meaning representation, knowledge representation, and reasoning in relation to getting computers to have that human-like language behavior. Language understanding and generation happen, I think we all know this intuitively, happen in the face of what some linguists call, and what I call, linguistic variation, the idea that, or the fact that there are many different ways of saying the same thing. I mean, I think everybody has heard that kind of phrase, or has heard that idea. And the central idea that I've been working on is this one, that a consequential part of the representations that we're creating and manipulating when we work with language, or when we think and talk, are actually non-linguistic or language-free representations. So the stuff, if you say there are many different ways of saying the same thing, there has to be some stuff that represents that same thingness that is other than language, that language maps onto, for us to realize, oh yeah, those two phrases or those two sentences mean the same thing. And I think there are imagery, embodied cognition representations that are completely different and separate from language. They map onto language. The mappings aren't one-to-one. And that's the most compelling way of, I think, of achieving this kind of non-linguistic representation, is by decomposing concepts into complex combinations of conceptual primitives, in a sense, building a separate non-linguistic system for representing concepts. And that's what you're seeing there in this slide on the right. On the right is this expression of a concept from the input in the system that you see there, language input on the left, in the system called conceptual dependency. And that's a decomposition representation that was popularized by Marvin Minsky, who was here at MIT for many years. And this system, this demo that I'm showing here in this slide, takes the input, translates it into this non-linguistic representation, and then from there is able to generate many outputs that are different in terms of the words and the grammatical structures that they use. And so when you have systems that do this transformation, I think it forms a substrate for rich relations between concepts and language expressions, and also between concepts, between thoughts and other thoughts, a rich representation for reasoning outside of language that I think people are using, or that I think people are doing. And that's the main base, the base of my research these days, is these kinds of representations, getting systems to work with these kinds of representations. Let me give you a little bit more depth about these kinds of systems. I said there's a system called conceptual dependency, or I'll often say CD, that you saw in that picture on the right there, which was a decomposition of that phrase that you saw in the input. Let me tell you more about that system. It tries to decompose ideas into combinations of conceptual primitives. Let me talk for a moment about those primitives and how they work. So this CD system had these primitive acts for physical actions. Let me show you what those were. So at the time that they came up with these, they were programming with very simple computers, so they shortened the names of lots of their variables. So P-trans is short for physical transfer, and it means that it's a physical primitive, meaning that something is traveling from place to place, or maybe a person is changing location. There's a primitive called move, meaning an animate object or person is moving a part of its body. There's one called grasp, meaning that two objects are moving together or attached together in some way, or something is grasping another thing. There's a primitive called propel, meaning that something is striking another thing or applying a force to another thing. There was a primitive called ingest, which meant that an animate object or being was taking something into its body. And then another one called expel, which is kind of the opposite of ingest, meaning that something, that an inanimate object is taking something or moving something outside of from the inside of its body, outside of its body. And part of the idea of this game of having these abstract conceptual primitives is that you try to keep the number of primitives small and express more things with less primitives by decomposing things more and having more complex combinations of those primitives. Let me show you what I mean by that. And let me give you an example of these kinds of decompositions. So let's say you wanted to decompose the sentence, Lisa kicked the ball, in this CD form, conceptual dependency form. So here's how you might start. You have a propel primitive act that's going to occur. The actor for the propel is going to be Lisa. That double arrow is a special relationship between the actor and the primitive act. There's an object case represented by an arrow and a little O here. The ball is going to be propelled by Lisa. Okay. And so all this says is that Lisa struck or applied a force to the ball, but it doesn't say anything about how that happened. So you add more primitive acts to the structure in order to kind of flesh it out more. So let me add another primitive act here, kind of a secondary primitive act, which is a move primitive act. Remember, move is an animate being moving a part of its body. The actor here is Lisa. And the object here is, there's a syntax here for foot of Lisa. So it means Lisa is moving her foot. And there's also a direction case represented by this D and an arrow, meaning that Lisa is moving her foot towards the ball. Finally, there's a link between these two primitive acts here, represented by this arrow and an I. I was short for instrument in this system. And so what it means is that the act of Lisa propelling the ball was made possible. The instrument for performing that act of propel was Lisa moving her foot towards the ball. Okay, so that's one example of one of these kinds of decompositions. Now let's try another one. Let's do another one of these, but this time I'd like you, maybe a little audience participation. Maybe you can try to give me the English sentence that it represents. Okay, this one has an ingest act, an ingest primitive act. Amy is the actor. The object is air, and there's a direction case to the ingest. Remember, ingest means an animate actor taking something into their body some way or another. And so the direction case has lungs of Amy. And then there's a second act here, a move primitive act, and the object of the move is Amy's chest. I guess it means Amy's chest muscles. The actor is Amy, and there's an instrument case, so it means that the ingest act of moving air into the lungs was made possible by Amy's movement of her chest. And so the question to you all is, and I think there are a lot of you here in the chat, but I see already people are getting the idea. Amy takes in air, Amy gasps, Amy breathed deeply. Okay, exactly. All right. So I think you all get the point. So I have here this gloss. Amy took a deep breath. So it could be either a noun or a verb, but I think you all get the idea. There's a question here. What does D represent again? So D represents the direction case in this system. I see another question. Would these types of structures also be able to help with translating between languages? Yes. Yes. Okay. Good question. Well, let me move my chat window so I can see for a second. Okay. All right. So you all, I think you all get the idea behind these primitive decomposition systems. So let me talk more about some of the current technologies that are out there for natural language processing or understanding. One place where people have made lots of gains is in building AI systems to do things with language, applying this thing called machine learning that I bet you probably have heard of, applying machine learning algorithms to large collections of language. And collections of language, you'll often hear we use the word corpora or corpus to describe a collection of language. I wanted to show you an example of a natural language processing and generation technology that's become really popular and well known in the media. It's based on deep learning, which is a machine learning technology, which is based on another thing called an artificial neural network. this technology basically tries to loosely model the way cells in your brain work, and it creates millions or billions of modeled cells of the brain to try to get systems to learn to do things. And these systems are amazing because if you look at the output, they seem to have the ability to generate language that really looks like it was written by people. A writer from the New Yorker ran a test of a deep learning system called GPT-2. There's actually a newer version of that system called GPT-3. This is an example from a couple of years ago, but really the same things are happening with the newer versions too. You give this system a passage of text, and then what it'll do is kind of generate a continuation of your text in natural language in the same genre and hopefully talking about some of the same things. They gave it a paragraph from an old New Yorker article about Ernest Hemingway from the 50s, and they had it generate some things. And I want you all to take take a look at this continuation created by this machine learning system, this deep learning system called GPT-2. And I think right in the chat, anything as you read it that sounds weird or strange or wrong, perhaps. I'll give you a second to read it over. Right. I think a lot of you have already remarked about the puddle of red gravy in the yard, question mark. Okay, great. I think a lot of you have pointed out things that I think I would have pointed out. I had another slide where I had like marked off some of the things that looked weird in this passage, but I think it's easy to find things that are weird. The red gravy, or the stuff about smoking cigarettes and needing to cover your hands or something. Yeah, covers face for wrist burns. Okay, so the point I want to make here is that in these systems, when you scratch the surface a little bit, look a bit closer, you start thinking, okay, are these systems really understanding what they're generating? Are they generating stuff that makes sense? These systems are called large language models because they have a lot of parameters. They represented by neurons, and they're trained on large corpora, large collections of language text. And so they're able to, my thinking is that they're able to model the text well, but they're not actually able to model the thinking well. They generate things that really look convincing as text, but as you start to look deeper into it and think about what they're really saying, a lot of it doesn't quite make sense. And so, like I said, again, getting computer systems to work with language isn't 100% about the language. It's really, a lot of it is really about the thoughts, the ideas that the language causes or evokes, and whether those thoughts make sense and connect with our experience. If your only experience is you've seen a lot of text and you're modeling text like these systems are, but they haven't really had world experiences like you have, these are still important challenges for getting these systems to work and understand with language. Earlier, I showed this figure. I showed this figure to talk about how language understanding and generation happen in the face of what linguists call linguistic variation. And paraphrase, recognition, and generation are things that people do that exemplify this phenomenon. So I wanted to give you a more detailed look at a recent study of paraphrasing, where we work to gather some better empirical evidence to support some of the basic claims that I've been making about, reasoning and understanding. Representation needs to be, at least a part of it needs to be non-linguistic. In this study, some preliminaries first. As part of our exploration, we theorized about two competing paradigms that cognitive systems might or do engage in when performing paraphrase tasks. So one is the surface alignment paradigm, and I've named it that. Basically, what it means is that meaning exists entirely within language. There is no non-linguistic component to meaning. If you're looking at paraphrases, for example, these are simply what we call equivalence relations between sentences, between lexical and syntactic language forms. And the main task for building systems is to build systems that have sets of expressions that define a meaning equivalence relation. So there's no non-linguistic component. There's no separate meaning. They're just relations between sentences in this paradigm. The other paradigm is the deep understanding paradigm, and that's the paradigm that I espouse. Says that part of a meaning representation is structures and processes that are not part of the expression of the language expression. They're not simply logical assertions that use words in the original expression, but there are these language-free, non-linguistic, cognitive, symbolic structures like the kind that I was showing you earlier. Although they correspond to language expressions, they don't resemble them, and they don't map onto them one-to-one. So to support the claim, I wanted to talk to you about this study where the main cognitive task that these cognitive systems were performing is this paraphrase relationship, recognizing a paraphrase relationship between two sentences or between linguistic items. And the main claim is that the deep understanding paradigm is a consequential part of the way people form meaning representations for paraphrase detection. And the methodology for this study is to support the claim is to basically compare the surface alignment and deep understanding systems on paraphrase tasks. So we'll look at paraphrasing, we'll look at these different systems and how they can look at pairs of linguistic expressions and determine that they mean the same thing. One preliminary thing is I want to talk about difference metrics for sentences. So it'll be important for us to look at two sentences and say that they're very different in terms of the words that they use. You'll hear me use terms like lexical or syntactic difference. Lexical is a fancy word that refers to the words that are used, and syntactic refers basically to the grammatical forms of a sentence. So there are a couple of different surface difference metrics that we use. One is lexical edit distance. Basically, for that one, for any pair of sentences, for example, the lexical edit distance is the minimum number of additions or deletions or substitutions of words to transform one sentence into the other sentence. Jacquard distance is another one. That one, it says here cardinality of disjunctive union. What that one basically is you take the number of unique words in one sentence in sentence X and the number of unique words in sentence Y that don't exist in sentence X, and add those together, the number of those together, and then divide out by the total number of unique words among the two sentences. So this distance metric is more sensitive to whether two sentences are using the same words. There's another metric that you'll see me use called BLUE, the bilingual evaluation understudy. It's like the Jacquard metric, but it's even more sensitive to if a sentence uses the same word more than once. The weird thing that you'll see in a moment is that this metric is inverted. So a high number for the BLUE score means the sentences are exactly the same, and a low number for the BLUE score means that the sentences are different. Someone asked a question about machine translation, or about whether you can translate between different languages using the system. And actually, this BLUE metric is used to evaluate machine translation systems. So next, I wanted to talk about, we built a corpus of paraphrases to represent the deep understanding paradigm. On the left, there is some computer code representing that decomposed non-linguistic structure that I was showing you earlier. And then here on the right are, based on that non-linguistic structure, some paraphrases that we generated based on that structure. So basically, this is the same system that I was showing you in the earlier slide, but then we enhanced it and turned up the volume on it. We were able to generate a large number of paraphrases of this one idea: John died because he could not breathe. We generated about 430 paraphrases of this idea using the system. Here are some examples of them. And then we combine those together to create paraphrase pairs. What's interesting is that the paraphrase pairs are very different from each other lexically in terms of the words they use, in terms of the grammar that they use. Okay, here's the system that we used for the surface alignment paradigm. There's a paraphrase corpus called the MRPC. Oh, sorry. Yeah, let me know if there's an important question. So basically, this corpus has about 6,000 sentence pairs, and they were constructed through this interesting process of alignment. What they did was they realized that at the time, there were these services, these news aggregator services that on the web that were aggregating, clustering articles about particular events that were happening. And so basically what folks did was they exploited the clustering algorithms that were being used. And so they found articles that were describing the same things that, and also they were topically and temporally related, describing the same things at the same time, and said, and what they tried to do was match sentences from those articles to make them into possible paraphrase paraphrase pairs of sentences to put in their corpus. They use an algorithm for doing this, and they came up with candidate paraphrase pairs based on lexical edit distance, and also the sentences had to have 3 words in common. And then they had human experts look at these paraphrase pairs and judge whether they were paraphrases or non-paraphrases. And so through that, they came up with about 5,800 sentence pairs. Some of them were paraphrases, some of them were not. Here's an example of a pair of sentences from this data set. You can see that I think a lot of the time what happens is that when someone publishes an article about something, they sometimes take an article that they published previously and then switch some of the words around. So if you look at these 2 sentences, they use exactly the same words, but they swap some of the phrases. But this is just an example of the MRPC corpus. I might come back to this later if I have a moment.
Jamie, there's a quick question from Bueni on the talks about question related to training data. Bueni, do you want to ask your question? I'm sorry if I'm mispronouncing your name.
Yes, that's close. It's Bueni. I wanted to ask, when working on a project related to language processing like this, does your team include a variety of disciplines like computer scientists and linguists, or is it mostly just computer scientists?
That's a good question. I would say there's some computer scientists. I think the most close discipline, other than computer scientists in terms of people that I end up working with, and also some of my training, is human factors. When we have to do studies with human participants, that there's some special, I think, techniques and skills related to that. Yeah, so there isn't. We don't often work with. I don't often work with linguists, but I would like to. I think it is an important discipline nearby for this kind of work. Yeah, it is. It is very interdisciplinary work.
All right, thank you.
You're welcome. Yeah. So so that describes the corpora or data sets for each of those paradigms. I next wanted to talk about the paraphrase recognizer systems that represented those paradigms. For the deep understanding paradigm, our paraphrase recognizer is people, and we hypothesize that people are doing this deep understanding thing. So we performed, as I was just mentioning about human factors, we performed human participant studies, and we had each human participant view sentence pairs from the deep understanding paradigm. These are called I call this the BABEL paraphrase corpus, because the system that we used to generate it was called the BABEL system. They also viewed sentence pairs from the MRPC data set. And then we also had a number of attention check pairs. So these were pairs of sentences that were very, very, very different from each other, could never, ever be considered paraphrases. We just had them in there to make sure that our human participants were paying attention to the task and not just answering randomly. And then we started with 100 human participants in the study, and we gave them some BABEL sentence pairs that were evenly spaced in terms of their distance metric, the Jacquard distance metric, which is more sensitive to whether sentences are using the same words. We gave them also a bunch of MRPC sentence pairs, and we also gave them some of these attention check pairs to make sure that they were paying attention. But then we realized that it would be important for us to really get good coverage of what our human responses were to pairs of sentences that really were different in terms of the words they use and the grammatical structure that they use. So we got a few more participants, about 108 more participants that only that mainly looked at, in terms of their BABEL sentence pairs, looked at ones with high Jacquard distance and then low BLEU scores. BLEU score is kind of inverted. Low score means that the sentences were really different. But basically, we tried to get better coverage of pairs of sentences and paraphrases that were really different in terms of the words they use in the grammar. Okay, and then finally, for the service and alignment paradigm, we for a paraphrase recognizer, we chose a system called BERT. BERT is BERT is kind of a complex topic. I won't go too deep into it, but I talked earlier about the system GPT-2, which is an artificial neural network system. BERT is also an artificial neural network system known as a general purpose architecture for natural language understanding. It's a neural network model with 100 million total parameters. And we trained BERT on the MRPC data set. So BERT is then going to learn how to try to recognize paraphrases based on a set of paraphrase data that was collected using the surface alignment paradigm. So it really would represent paraphrase recognition based on surface alignment. Okay, so sorry, just recapping, because I've hit you with a lot of stuff. We're going to juxtapose, one, the surface alignment corpus of paraphrases, which is MRPC, the surface alignment paraphrase recognizer, BERT, with the deep understanding corpus of paraphrases, which is this BABEL paraphrase, which was generated from this non-linguistic structure. John died because he could not breathe. And then finally, the deep understanding paraphrase recognizer, humans. For one last thing, though, for our studies with humans, when we had them look at a pair of sentences and give us their judgments, we thought, rather than just ask people to tell us, are these paraphrases or are they not, we used a scale. We had them give us their answers based on the scale called the semantic textual similarity scale, which gives us a bit more finer grained information about what people thought in terms of the sentences. So you can see a score of 5 means the sentences are completely equivalent. Then there's mostly equivalent, roughly equivalent, and then there's not equivalent, a couple of different, a few different levels of not equivalent. So it gives us a little bit of finer graining in terms of results from our human subjects. All right, our results, and then I'll wrap up soon after this. So one thing we're interested in is, were the paraphrases that we generated using our non-linguistic representation system, did people think that those were really paraphrases? And yes, they did. So those were the BABEL paraphrases, and so 92% of the answers for that were completely equivalent. For MRPC, actually, interestingly, for a lot of those sentence pairs, for more of those sentence pairs, people thought they were mostly equivalent, but not completely equivalent. So we're actually doing better than the MRPC data set. We also isolated a subset of the BABEL paraphrases that we call BABEL Max, and these are a subset of the sentences that have the high Jacquard distance that use very different words. And so the scores for that were also still very high in terms of people thinking that they were completely equivalent. So that was good. Our paraphrase, the paraphrases that we generated appear to be paraphrases according to people. Now, what about BERT? So BERT is this deep learning system that's trained on MRPC. For small Jacquard distances, BERT, for sentence pairs where the words were very the same, BERT classifies them, most or all of them, correctly. But when the lexical distance, edit distance, or when the Jacquard distance gets high, the accuracy of BERT falls pretty rapidly. And we found a statistically significant correlation between the edit distances or the surface distance metrics and BERT's ability to recognize that the sentence pairs in the BABEL sentences, which are all paraphrases, they all mean the same thing. John died because he could not breathe. BERT dropped off pretty rapidly. This is our main result here. So the x-axis is the blue score of the sentence pair in the BABEL corpus. Remember, the blue score is inverted, so high score means the sentences are the same here on the left. When you head towards the right, you're getting sentences that are much, much different in terms of the words and the grammar used. And then the y-axis here is the classification accuracy ranging from 0 to 1. And so what we found is that in red, you have the classification accuracy of humans, and in blue, you have the classification accuracy of the BERT model. And you see that the human classification accuracy remains high as you head from left to right, as you head from sentences that are almost exactly the same to sentences that are very different in terms of the word and the grammar used to say the same thing. While on the other hand, BERT is not like that. Well, we think that humans are actually processing a meaning representation that's similar to the one that we use to construct the BABEL sentence pairs. And BERT is not good at doing that. After a certain point headed towards the right, the accuracy is about 0.5. So basically, BERT is almost just flipping a coin to determine whether the sentences have the same, mean the same thing or not. BERT appears to be just guessing about it. So that's our main result. It appears that BERT isn't like people when it comes to this kind of thing. One thing you think is BERT's behavior just a reflection of the training data? We saw these sentences before. They have a high edit distance, right? So they might end up being chosen as candidate paraphrase, a candidate pair of paraphrase sentences. And I think most human experts would look at these and say, yeah, those mean the same thing. What I'm saying here, I guess, is that the MRPC paraphrase data set, the way that it's constructed by looking at news articles about the same thing, may not be the best representation of what it means for two sentences to be paraphrases. If people are largely republishing articles about the same thing and then just changing things slightly or something like that, it may not be a good representation of what paraphrasing really is. A deep learning system can exploit this and score really well on the data set, but it isn't really understanding what the sentences mean. It just has to look to see if they use the same words, and then it'll say, oh yeah, those are paraphrases. Well, okay, wrapping things up here. So my main claim was that this deep understanding of non-linguistic paradigm is a consequential part of forming meaning representation. I hope I've given you ample evidence that this non-linguistic language-free representation, that it is this deep understanding paradigm is really the real deal. It's part of the way that humans actually construct and process meaning, or at least it's worth for some further investigation, and that I provided some evidence in the form of this study with human participants against this deep learning model. And that's pretty much all I wanted to say. I'm sorry if I read over time, but I guess I'll end here quickly. And it's such a pleasure to talk to you all. And I look forward to your questions and your comments about all of this. Thanks.
So Jamie, that's great. We do have a few questions. Maybe we can start with Jake, who wants to know how, well, Jake, you can ask your question.
Okay, so what sort of questions would you ask the model, the system, to differentiate systems that try to satisfy graders and systems that have like a real understanding? Like, are there any clever questions you could ask to tell between them?
Yeah, clever questions to ask. Yeah, what would I do next? I mean, what I showed you is one set of clever set of clever questions to ask in the form of paraphrases. So there are lots of folks out there who have done studies where basically they take one of these deep learning systems and they do try to ask it questions usually about physical things. So some folks at NYU have done things like that. So let me maybe if I can show you a slide here. Let me. Yeah, so here's an example of something that I've been working on more recently. No, that's not the right slide. Sorry. Okay. So this is a data set called ProPara, and it contains lots of paragraphs about physical, chemical, biological, and geological processes. So this is something that I've been looking at more recently to see if I create these non-linguistic models of these kinds of processes, maybe I could ask questions of a deep learning model about these things that could also reveal more about its depth of understanding in comparison to humans' depth of understanding of these kinds of processes.
So a system that can paraphrase should be able to answer like non-paraphrase questions.
Yeah. So
okay.
This data set has you can see it has these descriptions here. And so what if we generated paraphrases of these bullet points of this paragraph describing how caverns form? Would a system that was trained on the original understand our paraphrased version of the description of how caverns formed? Yeah.
Great. Okay, Meta has a question on potential uses of this technology. Do you want to ask your question, Meta?
Sure. Yeah. So I was wondering if this research can be used to make a new programming language that's very similar to how we talk, so it's more accessible.
Yeah, exactly. Yeah, I think I mentioned it at the start of the talk, right? Wouldn't it be great if we could talk to our computers in natural language, in English, Arabic, Chinese, or what have you, instead of having to program our computers in Python? I generally the hope or the ideal would be that if we build the right representations, like anything like the ones that I've been talking about or something similar, that our computer programs would have deeper understanding of what it is that we're talking about, And so it would lead us closer towards the goal of really being able to talk to our computers and our computers having a deep understanding of what we said, rather than and having that be the programming language rather than having to do it in Python. There may be in the future something in between, where we're partially talking in natural language, but also partially talking to them in programming language as well. Great question.
That's great. Piranha has a question about even beyond coding, what potential applications might be. Piranha, do you want to ask your question?
Yes, I thought your talk was really interesting, and I was just wondering what you think some future applications of these new technologies are. Obviously, beyond like Siri and Alexa and Cortana, like beyond that, like what do you think these can be used in?
Yeah, I mean, I mostly focus on these technologies for the sake of the science. Like really, what's motivating me is trying to understand more about how humans think, or how thought is represented within us. In terms of applications, I mean, you've seen all this stuff out there, like Siri, Alexa. Another easy one would be, if we had systems that understood more in depth a question that we were asking. For example, if we're searching for something, then I think our search engines and our information retrieval systems would be much stronger as a result. So that instead of me, you kind of have to, if you ever Google for things, you kind of have to develop a skill for how to pose the query on Google to get the things that you want. And so if Google had more of a deep understanding engine, would it be easier to use, and would it also be more effective as well? So that's one easy one.
All right, thank you.
Okay, talking about maybe adverse effects of some of this. Tianco, do you have a question? Like to ask your question?
Yeah, I actually had two questions. One being that since I actually find this type of technology research really interesting, because it could be used to kind of improve our communications with one another, especially linking, creating almost type of universal language to help different communications occur. However, one fear I have with this type of research and technology is with a deliberate usage to distort or misinterpret information. Is one of the biggest fears, I think, with all future technology is with hacking and things on that line. Is there any type of safeguards or preventive gates that's being researched to help prevent this type of things from happening?
Yeah, I think the questions that have been raised, a lot of questions have been raised recently as we've seen more powerful artificial intelligence technologies about the ethics of having them and of using them. And in fact, the system GPT-2 that I was showing you examples of earlier, the proprietors of it for a while weren't allowing researchers access to it because they were worried that it could be used in nefarious ways. Generally, I think when it comes to technology, I mean, my focus again is I'm not particularly interested in using the technology. I'm mostly interested in the technology from the standpoint of what we can learn about human intelligence from it, and make and understand us better, and hopefully improve society from that standpoint. Like if we understood human intelligence better, how better could we help people and make lives better for people, not from the standpoint of giving people a technology that they can use, but understanding human psychology and human society from those perspectives. I generally think that if the fears that we have are maybe a reflection of issues and problems in our society anyway, that that anything could be so turned around and used as a weapon or used to do bad things. And so my thinking or my hope would be if we're better educated, then ideally we'd learn more about what's motivating people or what's driving people to take any technology that you have out there and then use it to do something bad to hurt others. That would be my hope. But otherwise, there are folks out there who are trying to study the issue of how to stop bad uses of technology. It's not exactly my expertise.
Got it.
But
Thank you so.
But I tried to give you my thinking on the issue.
Got it. Thank you so very much for the insight.
We have one last question, and that's on how students might be able to get involved. So Krishnaveni, could you ask your question, please?
Yeah, so I first I wanted to take a minute to say thank you for doing this presentation. I thought it was really interesting, and I really learned a lot from this presentation. And I was wondering if there was a way that we could get involved in your research.
Sure, yeah. So Smith College is a small liberal arts college. By the way, I enjoyed giving this presentation to you all. Thank you so much. So Smith College is a small liberal arts college focused on women's education. So we only have in our computer science department, we only have undergraduate students, and not graduate students who already have a college degree and are working on a PhD. And there are lots of ways that students have been involved in my research. A lot of I think as someone brought up earlier, there's a high interdisciplinary nature to this work that involves studying human artificial intelligence, these cognitive systems, human cognition, cognitive science, linguistics, human factors. In some respects, philosophy is important, especially when it comes to the issues of ethics. And so there are lots of ways, particularly when it comes to the interdisciplinary components of it, which, if I'm just a computer scientist, it's hard to cover so many disciplines. So one of the ways where I've gotten help from students is with collaborations across disciplines, and reviewing and understanding literature, because there's just a vast amount of literature on the topic of artificial intelligence. But then also there's we're building systems, so we need people who can program. We need people who can program in this language called Lisp. That was the language that things were expressed in that one slide. That's another place where we need help. And then also we run studies using with human participants, and we use crowdsourcing platforms largely to run our studies. And that's another place where students have been active participants in the research, putting together a study and then running it online using a crowdsourcing platform.
Thank you so much.
Thanks. Well, right now I'd like to ask Manya and Evan, if you could please thank our speaker on behalf of all of the students and present him with his gift.
Yeah, I can start first. So I just want to take a moment to say thank you for spending your time with us today and, just educating us about this topic. We're just all really grateful that you're here. And for me, this was really interesting because I'm doing the CogWorks course at BWSI today, this summer, and it's about autonomous cognitive assistance. So some of the things that you were discussing today kind of overlapped with what we were talking about. So it was just really nice to learn more about that. And I really liked what you talked about, the linguistic items and the activity that we did in the beginning. It was just really fun to know about that in a nice way. So yeah, Evan, you want to add something?
Yeah, thank you very much for spending your time and giving this seminar. I found it really interesting to learn about the non-linguistic representation and about like the deep understanding paradigm. And as Manya said, in the Cogworks course, we're also going to be learning about language processing with machine learning. So it was very nice to have like a preview on the topic. And then
My pleasure. Thank you so much. Yeah, here's my shirt. Thanks for the shirt.
Can you all smile? I'm going to take a picture right now.
Okay.
So hold on one second. Great. Thank you.
Excellent. Well, Jamie, thank you very much
Thank
for
you
your
very
time.
much.
And students, please do not hang up. Stay on for Lisa. But Jamie, thank you. This was a fascinating talk. Thank you very much.
Thanks for having me. It was my pleasure. Great to meet you all. Take care. Have a great summer. Bye.
You.
Thank you.
Yeah.
Students, don't go anywhere. I see you all going. Stop. Okay, so 3 quick announcements. When you send us emails, we get a lot of emails a day. It's very hard when you only send it to one of us. So if you could make sure you send it to the BWSI-admin account, that's great. That goes to me, Bob, and Joel. So whoever can get to it the quickest, we'll make sure that you get an answer. So I'm putting it in chat right now. Bob beat me to it. Joel did too. So that is the account thing. Anytime you guys send us an email, it should go there. Also, if you're having email issues with the MIT account, I can't help you. I get very many questions every day because people have locked out, forgot their password. I can't help you. You have to go right to MIT. I put that email address in there as well. So if you have email questions about your MIT email, you should be going to mit@service-now.com. So Monday, we're having the director of Lincoln Laboratory give his talk. And so that is when we take our official group photo. So that will happen during this seminar. So we would like for you to all have your BeaverWorks t-shirts on and know that we're taking a photo. So look your best because that is the photo we will use for everything, most likely from this point forward. So during that meeting, I need to see your faces. So I'm looking at a lot of ceilings, a lot of walls, a lot of ceiling fans and lights. I need to see your faces during that meeting. So please make sure you have your t-shirts and we can see you. If you did not get it, please email us so I can send you another one. But please just wear a black shirt if you have one. So just a plain black shirt, or, you know, a black, it doesn't have to be plain, but because we'll probably only see from your shoulders up. But make sure just wear a black shirt that day. And I think that is all I have. So have a great weekend. Hopefully, oh, I had one more thing. We do have an Instagram and Twitter account. It is MIT BWSI. If you aren't following it, please do. And then if you're posting anything about the program, hashtag BWSI and tag us in it so we can reshare it. So please, as you can all hear, my phone is going crazy because you're all starting to follow me right now. So please continue that. Use us, tag us. We love to see what you guys are doing. We want the world to see what you're doing. So great. Have a great weekend. And we'll see you all soon.
Thank you.
Bye.
Thank you.
Thank you.
Oh.
Thank you.
Thank you.
Thank you.
Wait, could you repeat where we should follow you again? I wasn't really able to hear.
MIT BWSI on Instagram and Twitter.
Oh, okay. Thank you. Bye.
You're
Have a
welcome.
good day.
Thanks.
Hi, Lisa.
Hello.
So signing off.
All right. Bye. I think we're good.